Good afternoon, good morning, good day, whatever it is. Today, for apportionment, we're going to be looking at a second method. This is going to be called the Lowndes Method of Apportionment. Now, yesterday, we had the Hamilton Method of Apportionment. Historically speaking, the Constitution was passed, the very first Continental Congress met, 1789. They were given the task of coming up with a way of apportioning the House of Representatives and taxes, therefore, to the newly formed United States government. Now, Hamilton put forth his method, the largest fractional part, where we took a look at the largest decimal and assigned based upon that. That was passed through the representatives, passed through the Senate, made its way to George Washington's desk. He said no. There's actually a separate method called Jefferson's method that we're going to see later on that was initially adopted. Now, politically speaking, Jefferson's method favored the state of Virginia, which is where Washington and Jefferson lived at that time, whereas Hamilton's method, based upon the largest decimal parts, tended to favor the northern states, those that had the larger population centers. The Hamilton's method eventually came into play, and it was used throughout most of the 1800s. It was used in a way that it also lined up with Webster's method. And by lined up, what I'm going to say is, we'll see this later on, that a lot of numbers were chosen because they worked out neatly, where they rounded appropriately. So rather than just saying we have 400 representatives in the House of Representatives, we are going to figure out some numbers that work, and then we're just going to say that's how many representatives we need in the House. Today's method, what we're going to call the Lowndes method, I've got here on the left, is the method of largest relative fractional parts. And so it's similar to Hamilton, but it's just a little bit different, this relative fractional parts. The Lowndes method was proposed 1832 by Samuel Lowndes, a congressman from South Carolina in the 1830s. It was suggested because the relative fractional parts gives preference more towards those states that are a little bit smaller. What we're going to do is we're going to compare the decimal portion to the number of current seats that a state already receives. Thus, the smaller number of states, if you have the smaller number of seats, you're going to have a smaller divisor that we'll see, and that will give you a larger relative fractional part, helping out some smaller states. This was proposed by Samuel Lowndes. South Carolina, there is a lot of angst between the northern states and the southern states at the time in the 1800s, and this is a way that the agrarian economy was trying to find some more representation. There's the argument that those northern states that had the heavy population centers, the industrial centers, were making all of the decisions for the agrarian South. The way the South counted people may have been an influence on that, but I'm not going to get into that right now. So Lowndes' method, similar to Hamilton's method. In going through and conducting a Lowndes apportionment, as always, we're going to determine the total population, we're going to determine the natural divisor, and we're going to find the natural quotas for each state. I'll put that in here. So we have 3 counties in Delaware. We are going to apportion 76 seats for this section. Spelled that wrong. So I'm going to go over to the calculator. We've got, I can't add today. I know that's wrong. We've got our total population. I'll put that in. I'm going to use that to determine our natural divisor. The natural divisor, once again, is the total population divided by our house size. We have 76 seats we are apportioning. Divide by 76. We get our natural divisor of 777.55. So again, that was 59,094 divided by our house size, 76. So our natural quotas, we're going to have a natural quota for each state That's going to be the state population divided by the natural divisor. Go back over to the right. This is the decimal number of seats that a state would receive. We can't have 24.33 or 25.32 or 26.35 representatives. We can't have a portion of a representative. So what Lowndes method does, once we have the total population, the natural divisor, the natural quotas, just the same as Hamilton, going back to step 2, we're going to round down the natural quotas. Then we're going to determine what we call the relative fractional part. Here, Kent, 24.33 is going to round to 24. Newcastle, 25.32 is going to round to 25. Sussex, 26.35 is going to round to 26. If we add together, we currently have 75 seats. Let's get rid of that. 75 seats. We need 76, so we have one more that we require. Now, Hamilton's method looked at the largest decimal piece. Lowndes' method instead is going to go by the relative fractional part. Now, the relative fractional part is the decimal piece divided by the integer, divided by the whole number. So for Kent, we're going to do 0.33 divided by 24. It's going to be the decimal piece divided by the integer. So we have 0.33 divided by 24. Our relative fractional part is therefore 0.01375. Take the decimal piece divided by the whole number. Do each one and I'll write that in. So the next we have 0.32 divided by 25. The decimal piece divided by the whole number. And lastly, 0.35 divided by 26. Those are going to be our relative fractional parts. So we take the decimal piece of our natural quota divided by the whole number piece, the current number of seats. The idea behind this is that it tells really how close we are to rounding up the decimal compared to how many seats we currently have. This tends to favor the smaller states because you currently have fewer seats. If you have fewer seats, you have a smaller divisor that will then give you a larger quotient. So we've determined the relative fractional part for each state. We have determined the remaining seats. We're going to allocate the remaining seats in order of the largest relative fractional part. Fractional part. Now we see we had 75 total seats. We needed 76. We need one more. So I'm going to look at the largest relative fractional part. Here, 0.1375 is the largest of those values. So 24 gets rounded up to 25. The others stay the same. We've got a total then of 76. That's the Lowndes method of apportionment. Key difference here is our relative fractional part. I'm going to do another example. Take our numbers, going through the steps. Every single time, we find the total population. I'm going to go through, get my total population. Put that in. Our natural divisor, every single time we take our total population divided by our house size. Here I've indicated we have 40 seats. $17.15 is our natural divisor. Natural quota for each state. We take the state population divided by the natural divisor. That's that. So we're going to first round down, take our natural quotas, round down. 8.9 goes to 8. I don't care how close it is. 4.8 goes to 4. 7.5 goes to 7. 12.6 goes to 12. 6 goes to 6. We see we have a total now. 8 and 4 is 12, and 7 is 19, and 12 is 31, and 6 is 37. We still need 3 more seats. Our relative fractional part, take the decimal, we're going to divide by the integer. Stop typing it all in, so you can see it from there. We see we need 3 more seats. We're going to look at the relative fractional parts, the decimal divided by the integer, the decimal divided by the integer, so forth. So the largest relative fractional part is that 0.21. Notice that it is the smallest state as well. Not always, but it works out. So that was at 4. They're going to now go up to 5. After the 0.21, the next largest relative fractional part is that 0.1225. So that goes up to 9. And the third largest relative fractional part is the 0.0746. So that was at 7. It now goes up to 8. We've added 3 seats. We had 37. We've added 3. Everybody else stays the same. We have a total of 40. There we go. That is Lowndes' method, the largest relative fractional parts. Oops. Should fix that up ahead. Try it out. Let's practice up on the site.